Let's have a look at this question on alternating current. Question says a 40 microfarad capacitor is connected to 200 volt 50 hertz AC supply. So we take this very cute capacitor, its capacitance is given to be 40 microfarad. And we take this capacitor and we connect it across an AC voltage source. So this source is given to be of RMS value 200. So RMS voltage is 200 volt. And the frequency is given to be 50 hertz. Alright. The RMS value of the current in the circuit is nearly. So what is IRMS? This is the question. Some current is flowing through the circuit. What is the value of IRMS? Root mean square current. What is the value? Well, what is the formula for calculating IRMS? You would say this is very simple. This is VRMS divided by total impedance of the circuit. Okay? Yes. Now, how do we calculate the impedance? Well, that's very simple. We only have capacitor as the single element. And we know what is the reactance of a capacitor. This is 1 upon omega C. Do you remember that? Okay. So, in our question, the total impedance is also 1 by omega C. And we can see we are getting VRMS times omega C. Okay? Yes. Now, what is this omega? Omega is nothing but 2 pi f. 2 pi f. And we can see f is 50 hertz. So, omega will be 100 pi. 100 pi for this question. So let's see what are we getting. IRMS is coming out to be VRMS, which is 200 times 100 pi. 100 pi is omega, and then we have to multiply it by C, and its value is 40 microfarad. So let me multiply 40 times 10 raised to power minus 6. Alright, okay. And this value, if you calculate, will come to be approximately around 2.5. So RMS current is 2.5 ampere nearly. We can mark option A as the right answer for our question. Let's have a look at this question on simple harmonic motion. Question says, the phase difference between displacement and acceleration of a particle in SHM is. So some particle is performing SHM and we have to find the phase difference between displacement and acceleration. Well, what is the relation in SHM between displacement and acceleration? Tell me the relationship between displacement and acceleration, or acceleration and displacement. One and the same thing. You would say acceleration is given as minus omega square x. This is for SHM exclusively. Okay? Yes. Now we can see if x is positive, then A is negative. If x is negative, A is positive. So the direction of acceleration and displacement are completely different. Yes, this is always happening. So we can see from this equation itself that the phase difference between them should be pi. And we can mark option C as the right answer. Now if you don't agree with that, if that is too early for you to understand, I can give you an example. Let's say we have amazing SHM going on. A particle is at rest and we give it some velocity v when it was at x is equals to 0. Now what will happen? It will go to and fro. It will reach the maximum location. It will reach the original position, then the minimum position, and then again the position x is equals to 0. So this is the to and fro motion. This is SHM. And we can say for SHM, we have x is equals to a sine omega t for this case. If we differentiate that, we will get velocity, and we can see it is coming out to be a omega cos omega t. Yes, okay. Now let's differentiate it further. What do we get now? We will get acceleration, and we can see it is coming out to be minus a omega square sine of omega t. Can you see that? Yes. Now instead of writing minus sign in front of everything, we can remove this minus sign and we can write sine of omega t plus pi. Wow! We can definitely see now the phase difference between x and a. The phase difference between x and a is nothing but pi. Can you see that? Yes. And you can also see what is the phase difference between x and v. We can write the velocity as a omega. Instead of cos omega t, we will write sine of omega t plus pi by 2. Now the phase difference between x and v is pi by 2. Wow! So we know phase difference between x, v, v, a, x and a, v. Everything. So option C is the phase difference between x and a. Displacement and acceleration, and pi radian is the right answer for this question. Let's see this awesome question on kinetic theory of gases, and this is an easy one. So question says the average thermal energy for a monoatomic gas is. Now what is the kinetic energy per molecule for a monoatomic gas? Let's say the temperature is T. So we can see for a monoatomic gas we have 3 degrees of freedom. Only 3 translation degree of freedom. And we can see the average kinetic energy per molecule is nothing but 3 by 2 kT. 3 by 2 kT. Here 3 is representing the degrees of freedom. Now we can see 3 by 2 kT should be the answer, and we mark option D as the correct answer for our question. Let's have a look at this question on photoelectric effect. Question says light of frequency 1.5 times the threshold frequency is incident on a photosensitive material. Wow! So we have a material, this is a photosensitive material, and let's say the threshold frequency is mu naught. Now we incident some light on this material like this. This light is of frequency mu 1, which is 1.5 times of mu naught. This is given in the question. What do you think will happen? Will the electrons get ejected out? Yes, they will. When the frequency is greater than mu naught, the threshold frequency, then the electrons are ejected out of the material and we see some photocurrent. So the question further says, what will be the photoelectric current if the frequency is halved and the intensity is doubled? What will be the photoelectric current if the frequency is halved and the intensity is doubled? So what are we doing? We are doubling the intensity, but we have the new frequency mu 2, and mu 2 is actually half of the older frequency, mu 1 divided by 2, that is 1.5 mu naught divided by 2. This is our new frequency. We can write it as 0.75 times mu naught. This is our new frequency. Now what do you think? Is this frequency sufficient enough to eject the electrons out of the material? No, it is not sufficient. Why not? Because if we want to eject the electrons out of the material, we require a minimum energy. The minimum energy of h times mu naught. And this frequency mu 2 is less than mu naught. This can provide a chunk of h times mu 2. And this is not sufficient to pull an electron out of the material. So, however intense this new light is, it won't be sufficient to pull out a single electron from this material. Therefore, there is no chance of any photoelectric current. Hence, we can mark option B 0 as the right answer for our question. Let's have a look at a question based on elasticity. And these types of questions are very easy because they involve a simple formula. So question says, a wire of length L, area of cross section A is hanging from a fixed support. So there is a fixed support and some wire hangs from that support. The length of the wire changes to L1 when a mass capital M is suspended from its free end. The expression for Young's modulus is, so we have to find what is the Young's modulus of this wire. Now I will tell you the entire story again. There was this wire once upon a time and its length was L. So we bring some mass capital M and we hang this mass from the wire. Due to the excess force on the wire stretches and the new length is L1. So we have to tell what is the Young's modulus Y of this wire. This is the question. Do we understand the question? Yes? Okay. Now, how do we solve this question? Well, let's try to remember the formula for stress. Stress, which is force divided by area, is equals to Young's modulus times strain. Stress is equals to Y times strain. Strain is change in length upon original length. Let's put the values and get the value of Y straight on. Now, as we hang this mass capital M, there is an excess force on this wire that is equal to mg. So we divide this by the area of the wire, which is given to be capital A, and this is equal to Y times strain. What is strain? Change in length upon original length. Change in length, as we can see, is L1 minus L. Can you see that? Okay. So L1 minus L, and we divide this by the original length, which was L. So from this we can see Y is coming out to be mgl divided by A times L1 minus L. Yes, this is our Young's modulus. Okay. Now we go and mark option B as the right answer for this question. Here is a question on optics. The question is very interesting. It is based on thin prism. The question says, a ray is incident at an angle of incidence I on one surface of a small angle prism with angle of prism A and emerges normally from the opposite surface. Wow. So some incidence is happening on the prism and some ray is emerging out of the prism. That's great. If the refractive index of the material of the prism is mu, then the angle of incidence is nearly equal to. So what all is given? It is said that the angle of the prism is A and the refractive index of the prism is mu. And when some light is incident, it refracts and goes on the other side, and from the other side it emerges at an angle of 90 degree with the prism. It emerges at an angle of 90 degree. Now finally at the second surface, can you see the angle of refraction is 0? Therefore angle of incidence will also be 0. So this angle will be 90 degree. Can you see that? Okay. Now let's talk about surface 1. What is happening at this surface? We can draw first of all a normal at this surface like this. Okay. Now the angle of incidence, let it be I. Angle of refraction, let it be R. Okay. So angle of refraction is R. Now we have to tell what is the angle of incidence I. This is the question. What is the value of I? This is the question. How do we tell that? Well, let me suggest you something. You can calculate what is this angle. What is this angle? This angle from the right angle triangle we can see is 90 minus A. Can you see that? Yes. And this normal makes an angle of 90 degree with the surface. So what is R? What is R? R is equal to A. Yes. R is equal to A. Now we will apply the Snell's law and calculate the answer. So we got everything right, and now it's time to apply the Snell's law. We can say that refractive index of the air is 1 times sine of angle of incidence I. This is equal to refractive index of the material, which is mu, times sine of R. R is equal to A. Very nice. Okay. Now let me suggest you something. Limit when x tends to 0. Limit of sine x when x tends to 0. What is the value? This thing is approximately equal to x. So sine of x, we can write it as x itself when x is very, very small. So we will use that to solve this question. Sine of A If A is very small, how can we write sine A? You will say we can write sine A as A itself. Yes. Now mu times A is roughly equal to sine I. Fine, fine. Now think about what should be mu times A. It should be really small or should be really large. You will say, well, if A is very small, mu times A is also very small. Yes. So this means sine I is very small. And when sine I is very small, we can write sine I as I itself. So I is roughly equal to mu times A. Understood? Okay, fine. So option A, mu times A, this is the angle of incidence, and option A is the right answer for this question. Let's have a look at this question on rotational motion. Find the torque about the origin. Find the torque about the origin when a force of 3 cap Newton acts on a particle whose position vector is 2 cap meter. Now what do we know? We know the force vector and we know the r vector. What do we have to find? We have to find the torque about origin. So simple. Torque about origin. Now, what was the formula for torque? You would say it is r vector cross f vector. Very nice. How awesome are you? R vector cross f vector. Nice. Now let's put the values and get the answer. What is r vector? R vector is given to be 2k cap. Awesome. What is f vector? F vector is 3j cap. Awesome. Now this thing is coming out to be 6. And then we have k cap cross j cap. What is this k cap cross j cap? Now let me tell you something awesome over here. You can mug this up. Write I, write j and write k. Then put some cap on top of them. Now when you do I cap cross j cap like this, if you move in anti-clockwise, then when you do I cap cross j cap, you will get k cap. And when you do j cap cross k cap, you will get I cap. So when you move in anti-clockwise sense, you will get everything positive. So what is k cap cross I cap? It is j cap, right? And if you move in clockwise direction like this, you will get something negative. So we can see k cap cross j cap, k cap cross j cap, this thing will be minus I cap. And our result will be minus 6 I cap. Okay? So remember this awesome anti-clockwise cycle. Everything is positive anti-clockwise, but things are negative when we move clockwise. So option A, minus 6 I cap, is the right answer for our question. Here is an interesting question on Young's double slit experiment. In Young's double slit experiment, if the separation between coherent sources is halved and the distance of the screen from the coherent sources is doubled, then the fringe width becomes. Wow. So the question is all about fringe width. And we have an interesting term, coherent sources. Now let's see what is the double slit experiment. So you can take a piece of paper, you can make 2 slits on the piece of paper. When you pass some laser light through this paper, then you can see light will emerge from these 2 slits. These slits behave as coherent sources, okay? And then you have some screen in front of this apparatus. Now let's say the distance between the screen and these coherent sources is capital D, and the gap between these 2 coherent sources is small d. In terms of capital D and small d, we will calculate what is the fringe width beta. Now what is this fringe width? What do we mean by fringe width? Well, you can define fringe width as the separation between 2 consecutive dark fringes. As you can see on the screen, there will be many bright spots and many dark spots. So distance, the separation between 2 consecutive dark fringes will give us beta. Or you can define it like this also, the separation between 2 consecutive bright fringes, one and the same thing. So this is beta. What is the formula for beta? This is lambda capital D divided by small d. So if we move the sources farther away from the screen is very, very far away, then we can see beta increases. If we move the sources closer to the screen, then the fringe width decreases. So this is how beta varies. Now, in our question, they said that the separation between the two coherent sources is halved. That is, we have a new separation now. We will call it d dash, and d dash is small d by 2. Okay? And they said that the distance between the screen from the coherent sources is doubled. So our new separation to the screen is capital D dash, and we will call it as twice of D. Okay? Yes. Now, let's apply the new formula. We will have beta dash as lambda capital D dash divided by small d dash. Okay? Okay. Let's put the values. We are getting lambda times, now d dash. D dash is twice of d. And what is small d dash? Small d dash is small d divided by 2. So we are getting 4 times lambda capital D by small d. Yes, this is 4 times of beta. 4 times of previous fringe width. So our new fringe width is 4 times of previous fringe width, and we can mark option A 4 times as the right answer for our question. So after a really long time, we get an easy question. This is based on atomic model. The question says, for which of the following Bohr model is not valid? Bohr model is not valid for which of the following options? First of all, before we talk about for which atoms Bohr model is not valid, let's talk about those atoms for which Bohr model is valid. Bohr model is valid for hydrogen-like atoms. It is obviously valid for hydrogen. Now, what are the hydrogen-like atoms? In the atoms, you can see one electron revolving around a positively charged nucleus. So, for example, helium plus, this is an hydrogen-like atom. Lithium plus plus, this is also an hydrogen-like atom, and the series go on. Okay, so let's look at each and every option. Let's find out whether the Bohr model is valid or not valid. Deuteron atom, this is also known as deuterium. In deuterium, we have in nucleus a proton and a neutron, and there is an electron revolving around this nucleus, so we get an atom. Now, for this, Bohr model is valid. Okay, for option B, singly ionized neon atom. What do you think? For this atom, is the Bohr model valid? Is there only single electron in this atom? No. There are many electrons. So for this, it is not valid. Option C, hydrogen atom. Yes, it is obviously valid for hydrogen atom. And option D, singly ionized helium atom. Yes, for these atom, it is valid. So only option B, singly ionized neon atom. For this atom, the Bohr model is not valid. So we can mark option B as the right answer for our question.